Thanks, Pork. So Pork's far ahead of me. When I say that I don't have any faculty positions, everyone pretty much leaves the room at that point. So as Pork mentioned, data science is this combination, statistics, computer science, a wide range of application areas. And I thought that in terms of statistics, I'd talk a little bit about Bayesian methods. Now, they've been around a long time. In fact, Reverend Bayes, for whom it's all named, was around the 1700s. And there was always been academic interest in Bayesian methods, and I'll say what I mean by that as we go. But it really is 1990 or so when computational algorithms and methods that had basically been developed in other areas of application were brought to bear and made Bayesian methods practical. And they've had a very big impact in a large number of domains. So this is some examples that I've used to say when it works, when it doesn't work, and so on and so forth. Also giving the new UCI logos. So let me start with an example that I love to show in almost all kinds of classes. These are kidney cancer death rates from a paper in the Journal of the American Statistical Association 25 years ago. And so there are 3,000 plus counties in the United States. This is the death rate in each county. The darker you see, the darkest is the top 5%, then the heavy gray is the next 5%, and then the lighter takes you down to 25%, and everything else is white. And so it's entertaining to look at it and try and come up with some of the hypotheses for what's driving these high death rates. And we don't have a lot of time, so we're going to skip the fun part. But it's a little surprising that everything's concentrated in the upper Midwest. It's hard to know exactly what the causal factor might be. So this fellow in Jazza did a Bayesian analysis, and again, I will get to what that means. And you can see that the picture actually changes quite a bit. And it turns out that if you think about it, what's going on here, the driver is not any environmental or other factor, it's actually sample size. Right? And you have a small county where a couple of deaths means the death rate is very high. You have a lot of small counties that have zero. It doesn't mean they have zero risk, they just have zero deaths. And so if you thought about saying, this is data, but I'd really like to understand the risk surface, what's going on across the country, this is clearly misleading, and maybe this is a little better. We don't know the subject area. I'll show you another example with similar data later. So, when I talk about Bayes, what do I mean? And so I think of it, and you can get as many answers as you can have Bayesian statisticians, but I think about it in terms of two key ideas. The first is that probability plays a central role, and I'll say a little bit more about that, not much, but probability is the language of uncertainty. We use it to describe whether it's going to rain tonight or not, tomorrow or not. And in statistics here, in Bayesian statistics, probability plays two roles. We usually have some kind of probability model that relates to data we can see, the death rate, to some unknown parameter that we believe, in this case, maybe the true risk of death. And then the second piece is a probability distribution that tries to put in other information. And other information could be things we know about the kidney cancer death rate from other studies, previous studies, or something like that. And then the second key idea in Bayesian inference is to try and draw conclusions about the unknowns from what we know on the knowns. And it's called Bayesian statistics largely because that's done with a mathematical result called Bayes' theorem. That allows you to flip the world around and say, I have data given unknown parameters, and I'd really like to, now that I've seen the data, say what I can about unknown parameters. I should say, for folks in the room who have done statistics in a lot of different fields, many things that you've already doing and thinking of statistics have both Bayesian and non-Bayesian interpretation. So it's not really all that different than what you know. And so this kind of spells it out into the three steps that correspond to those two ideas. The first is what I call a full probability model, and a little bit of, there's no math in this talk, but so this is some of the terminology that lives in Bayesian statistics. So the likelihood explains how the data relates to these unknown parameters that we're interested in. And then the prior distribution is what we know about these unknown parameters before we collect any data. And the machine here, if you will, is Bayes' theorem, which allows you to take those two pieces and turn them around and run it basically backwards and say, I know if I knew the parameters, I know how to get data. now I have the data, what can you tell me about the parameters? And the last step I always like to talk about because it doesn't get talked about a lot, and it's, how do we know that the various assumptions we made along the way make sense? And we need to check that constantly. And it's sad to me that people often leave that out. I built this great fancy model, I ran it, I got these great results, isn't this fun? Well, is it realistic to the problem? So probability, as I said, is the key thing here, and there's a lot to say about probability, but for today, this is the very caricatured description. Probability is a language for uncertainty. Basically, it assigns numbers between 0 and 1 to events. And events could be anything, the probability of winning the Super Bowl, probability of rain tomorrow, and the probability that someone who gets this treatment survives 5 years. These are all things that you might want to know the probability of. And they can be defined in lots of ways. Sometimes we have a physical argument, for example, to say why heights are normally distributed in the population. There are a lot of factors contributing to that. Sometimes we know because we flip thousands of coins, we know the probability of a head or a roll of a die. So there are frequency arguments. And sometimes it's just our opinion about what's likely or not. All of these are sources of information that might be useful in Bayesian analysis. So the piece of Bayesian inference that has caused some controversy over the years is the prior distribution. So this is the piece that says, what do I know before I collect any data? And many people find this a hard concept. They want science to be objective. So my opinion about the parameters somehow doesn't belong in there. But of course, what I'm going to show you today is you don't have to necessarily want to use your opinion. There are a lot of ways that Bayesian methods are helpful. There is a lot of information we have, and the question is how to get it in. And so the prior is this pre-data information about the parameters. And it could be an honest, you ask an expert, how likely is a patient to survive on this current cancer treatment? How well do you think the new one might help? You can get information from experts and try to use that in your study. You might have data from previous studies. So those are the kinds of things I'm thinking about. But it turns out, for me at least, what I'm going to talk about most is the prior information that may not actually be very precise about what's going on, but it may only be information that says, I don't know what the death rate is here, and I don't know what the death rate is here, but gee, they're awfully close together, and I bet they're related in some way. So we can even use information that's less precise like that. So the way that I set this up was to try to talk about 3 examples: small data, medium data, big data. But I realized over the last 24 hours that I don't really have time for 3 examples. So the small data one is going to be tossed out. But it's, I have a book that I'll refer to at the end. And this example kind of runs through the book over and over again. And it's a fun one for people who have kids in high school, like I do. So it's about SAT tests and how well different coaching programs run. So this is small data. It's only 8 data points. So I'm going to just tell you what's going on here. There's 8 studies, and if you look at them, the coaching program seemed to improve your SAT score by almost 30 points in School A on a scale of 800, and that's pretty good, and it's almost 2 times the standard error, so it's kind of statistically significant. But these other ones are generally not significant, and they're all over the place. So it's kind of hard to know what to make of it. And so the challenge for data like this is to figure out how to draw conclusions. But as I say, I don't want to go too deep into this. So I merely want to point out from this first example that you have 8 studies that have each been done independently, and they seem to lead to very different conclusions. And so one interpretation is some programs work and some don't, but another interpretation is maybe these are just 8 random representative programs, and School A is really not that good, it's just the best of 8. And School C's program is probably not really bad, it's just kind of unlucky sample in the study. And so you might think of these as 8 draws from a population of possible studies and analyze them in that way. So unfortunately, I don't have time to really walk through that, so I'm going to skip ahead to another one like the one I started with. So this is a project that I actually worked on with the National Center for Health Statistics, which is part of the CDC in Atlanta. And these are infant mortality rates. So these are children that die before their first birthday. And the average rate in the US, this is in the early 90s or the mid 90s, was about 7 per 1,000 births. But you can see there's a wide range, and again, these are by counties. And it ranges from 0 to 77, and again, the 77 is a county with very few births. And these are color-coded, and so again, you get a sense that a lot of variability. And probably not the best way to think of it as this is the best guess for the risk in this county, right? So there are counties here with very low rates, maybe surrounded by counties with high rates, and you don't necessarily believe it. So how can you think about this in a Bayesian way? So the first part's easy. The data are, there's some number of births, and some number of children don't survive the first year, and there are standard statistical models for that. It's a binomial data, something like that. The second level says, well, now I have this risk of death in each county. So there's 3,000 of these parameters. What do I know about them? Well, one thought that you could take is, and it's pretty common in analysis like this, is to say, I'm going to think about these 3,000 rates as being drawn from a population of possible rates. So, God, your favorite deity, however you like to think about this, randomly assigns rates from a population. But it means in particular that I need to realize when I see the data in a particular county, it's partly the rate that was assigned to it and partly randomness. So if I really want to understand the rates, I need to try and undo the randomness. And so I'm not going to show any details about how that happens, but you can fit a model that tries those two things together and says, now that you've seen this data, what do you believe the true rates are? And they're not exactly lined up, but you end up like this. Now, there are two things to point out. The color scale is the same. That is, the cut points are all the same. But the top value is much smaller now. So in fact, there's nothing that corresponds to the black here, which were rates of 16 or higher. The highest rate now is 15 per thousand, which makes a little bit more sense. You wouldn't think in the United States that you'd see so much variation in rates. And the other thing that's supposed to jump out is it's smoother, right? There's many fewer light spaces too, because many small counties with 0 deaths don't actually have 0 death risk. And so those kind of get smoothed out a little bit. There are still parts of the country that have higher risk than other parts of the country. The Southeast in particular stands out. But this is a very crude model. You could try to put more information in. And just to show you how this works, I've given not a random sampling of counties. So the top 2 counties, of course, are Los Angeles and Chicago. They have huge population. And in this, you can see the observed rate and what I estimate from my model, and they match. And this is one of the things I like about the Bayesian approach is when you have a lot of data, you don't have to rely on information from any other source. But if you look at the 3rd county in the list, King County in Texas, there were only 13 children born in the time period, and 1 of them died. So the death rate is 77 per thousand. Okay? Well, that's chance at work. And so you can see the estimated rate is 8.1 per thousand, which is above the national average, but not nearly as extreme as the data. And all 3 of these basically have high observed rates, but they all get lower rates now, and notice that it's possible to flip order even. That is, the county that looked the worst is not the worst anymore, because this one had a high rate and has a larger number of deaths. And you see the same thing in the last 3 rows, which are 3 counties of different sizes, all of whom had 0 events, but all of which have some risk. And how much you believe the 0 is indicative of good health outcomes depends on the population. So I want to say, I mentioned in an early slide that you have to decide what you're assuming and whether it's plausible or not. So deciding that all of these 3,000 rates come from one giant population is probably not realistic. You'd think whatever's going on might have more local phenomena. So I fit another version of the model that says, you know what, let's take the rates in a state as coming from a population, and then the 50 states come from another level. And you can see that you can see state boundaries here, which is not necessarily a good feature, but you can see them so that states that have high rates overall are now kind of helping each other get better estimates. It's merely to show an alternative model. Last thing here is to show you a picture of how to sometimes explain what's going on here. So these are raw rates here. The vertical scale is the infant mortality rate. And these models, the national model and the state model, give you estimated rates that are shrunk towards the population. So we sometimes talk about shrinkage. So I wanted to show one more example. So that was the first example. The second example is brain imaging data. It's actually work that I did with Porrick and a student of Porrick's. And it was done a very large grant that was headquartered at UCI called the FBurn, functional brain imaging. And it was multi-site. So there were, for this particular site, 5 sites across the country. And the same 8 people went to all 5 sites and did the same task. And brain imaging is used to study how the brain works in a variety of conditions. Schizophrenia was one of the ones we were interested in. But these are all control subjects, and it was done to understand the variability in brain imaging at different sites, because you'd like to pool data and get big samples that way, but you need to make sure. So this is one subject, 5 sites, 2 different days, and they did the same task 4 times on each of those days. And this is one slice of the brain, and light spaces are brain areas that seem to be activated by the task. So I'm just going to show you 3 slides, one of which is, or 4 slides. If you were just analyzing a single image, there are a lot of things you could do, and they usually try to find these circles, which are areas of activation, sometimes called hotspots. And so this is an approach we did for doing that, which looks for kind of Gaussian blobs. So that's one image. But now you could do that for all of the images. And so these are 8 images for one person at one site, and this is just a single 2D slice, obviously. And so we fit that model to each of these 8 and got very different answers. And so as I said with the disease data, you don't necessarily believe each one individually. You'd like to take advantage of the fact that this is the same person doing the same task, and therefore you'd expect activations in similar areas. Not just look separately at each image and not take that information into account. So the third line, which I've now added, assumes that there's a common model for all 8. And so that does a nice job, obviously, in creating a common story, but it may be too restrictive. Well, my whole talk sounds like the 3 bears, right? This one's too noisy, this one's too soon. So this one says, you know, there are these 2 areas, some people don't activate the black one. But as I said, that doesn't seem realistic enough. We expect some variation from day to day and from image to image. And so the last row actually still looks for common places across the images, but recognizes for a variety of reasons, both technical and biological, that they won't always be in exactly the same place in the same person on different days and in different instances. And so you see these images in around the same place, but with different sizes and orientations and shapes and the like. So Bayesian methods, that's a very, very fast overview, are useful when there's some information, aside from the data, that can be helpful, including this notion of relationships among units. They've been useful when there are many parameters, imaging as I just showed, genomic data, a lot of spatial data, and they're very flexible. As Porrick mentioned in his opening remarks, one issue with a lot of the big data analytic techniques is that computations can be really challenging. And so that's one of the things in Bayesian methods. So I've listed here 3 Bayesian textbooks at the top, 2 of whom have authors at UCI. 3 articles that I really like that get at some of the history of Bayesian statistics, and especially for this audience, the Leo Breiman paper is not at all about Bayesian statistics, but it gets at Porrick's discussion of statistics kind of thinking small and computer science thinking big, and how they kind of work together. And if you have any questions, 15 minutes is not a long time, 20 minutes, so I'm done.
Time for 1 or 2 quick questions.
Professor, you said that Bayesian methods can help with like missing data. Do you think it can help with like missing data spatially? Like if you had a county that didn't have data, or like traffic information that you didn't have in a region?
Yes, absolutely. And I always try to be, in this room I don't have to be too careful, but most everything I've done Bayesian can be done in other ways as well. So my argument for Bayes is it makes it easier to do those things. But yes, absolutely, you can do that. And In fact, a lot of spatial stuff done, say, folks who are looking for oil, discovered a whole bunch of techniques, Krieger is one name that it goes by, where you kind of spatially interpolate. And so those kinds of things are done in a variety of fields already, and so it can be done here. You can make a prediction. In a county where you have no data, you'll be more uncertain about it. But you can make a prediction. It's a great question. Thank you.